Okay, do
So
you
let me introduce our next speaker, Lucio Centrone from University of Bari, Italy. The title of this talk is on geometries arising from varieties of algebras. Please.
thank you very much. Are you able to see my laptop
Yes,
here?
it's okay.
Okay. So let me introduce a bit the environment of my talk. We are in the environment of PI algebras, algebras with polynomial identities. Maybe most of my talk will be concerned in the environment of associative algebras. Anyway, I can say, well, most everything should be adapted for non-associative stuffs too. Of course, I will comment whenever proper all such kind of things. So I would like to start a bit with this definition. We have a field, and we shall denote it by F, and we have an alphabet, X, which is a countable set of indeterminates. And we consider the so-called free associative algebra freely generated by X over F. And we shall call polynomials its elements. Okay. In this case, we simply took a set of letters, and we call a word simply the set of word that can be performed using such kind of letters. And we call polynomials their linear combinations. Simply this. This is, of course, a notion that could be, of course, be adapted in a non-associative case. So as I told previously, all the stuffs may be set in a non-associative environment. Okay, we have an algebra. We say that this polynomial is a polynomial identity for an algebra if it vanishes under all substitution of all elements of the algebra, which has been chosen by ourselves. So examples of polynomial identity. For example, if you are in an associative environment, well, any commutative algebra is an algebra with polynomial identities because it satisfies the commutators. Any Lie algebra, for example, finite dimensional, is an algebra with polynomial identities. Okay, we go further, and the set of all polynomial identities of an algebra will be denoted by id of A. Well, and it has a very attractive and interesting property. It is invariant under endomorphisms of the free algebra. It is called T-ideal. And of course, as almost all the structure we have the smallest T-ideal containing, for example, a set of polynomial, as in this case. This is called the T-ideal generated by S, and this guy here will play a crucial role not only in this talk, but in all the theory of PI algebras with polynomial identities, is called relatively free algebra of A. So just to recall the symbol here, we have free A is simply the quotient of the free algebra over the identity. So this is what we call relatively free. Okay, so we start presenting the first of the characters I announced in my title. So if we have an algebra, whatever you want, Lie, Jordan, associative, whatever you want, the class of all algebras B, satisfying all the identities of the algebra we have chosen, is called variety of algebras generated by A. Okay. Okay. So first of all, I would like to say you that I will show off three aspects of polynomial identities, which is a very well-known and well-developed already well-developed branch of mathematics. And in this talk, I would like to experiment three new point of views in the study of this theory. Well, in just to recall you well, a really small account on history of PI algebras. Well, it started with a very geometric set because it was really intimately related to the notion of the geometric notion of equivalence between two important theorems, the one of Papa Pascal and the Desargues one. So at the very beginning, well, the origin of the theory of PA algebra as a geometric set. So soon after, a theoretical aspect, as how to say, played a very prominent role in the study of PA algebras, and more or less at the middle 70s, mathematicians started to explore the combinatorial aspects of this theory, which involved also the theory of a representation theory of symmetric group. So, well, the very last part, from the point of view of the growth of the study of PA algebras, well, involved the study of varieties in the sense of their growth, in the sense of their classification, and classification with respect to the growth. And now I would like to propose you three new aspects. Okay, let us start off with the first one, identities of affine group schemes. So we have two categories, and we define a contravariant functor. Well, just to recall what a contravariant functor is, as a map from the first category, sending the object of the first one to the second one, and of course, mapping all the homomorphisms from the first categories to the homomorphisms of the second one. So this is what we call functor. And this guy here, functor from any category to the category of groups with its homomorphism, is said to be representable if there exists a guy here in the first, an object here in the first categories, so that FC is the homomorphism from C to A, where this guy is considered as a simplex. So we have right now the category of finally generated commutative algebra over a field, as we fixed at the beginning, and the category of abelian groups. And we say that a affine group scheme is a representable functor from this category to the category of group. And we have some, of course, we have some well-known examples. Okay, we try to extend our definition of polynomial identity to affine group schemes. And so we have a natural definition. We have a polynomial, and we say there's a polynomial identity for this affine group scheme, G, if it is an identity for the group algebra FGA for any A in the category of algebras. Okay, GA is a group, F of this group is a group algebra, and it admits the notion of polynomial identity. So just to recall, if F is of characteristic 0 and G is any group, the identity of any group algebra coincides with the identity of matrices of side n for some n. This is a very classical result. We have a theorem from Passman. Characteristic 0, G is any group, so the group algebra of G is Pi if and only if there exists a subgroup, an abelian subgroup of finite index. So, in few words, if there exists, if this group is virtually abelian. So this is the equivalent condition for a group algebra of being abelian, being Pi. So the question one can pose is the following. Is it true that a Passman result does hold for affine group schemes? Well, the general answer is no. But in what I would like to present, I would like to wiggle up a bit the hypothesis. And we say that a subgroup scheme of a group scheme, the initial group scheme, is said to be of bounded index if, of course, the image are a bounded index for serine n. So, what I would like to propose as a first step in this direction, we have this proposition. If G is an affine group scheme having a subgroup scheme of bounded index, then G satisfies the polynomial identities. And what about the converse? I mean, is it true that the if and only if condition holds in this case? Well, the problem is that whenever you have this affine group scheme, you're allowed, in a certain sense, to construct a subgroup scheme of finite index. The problem is how to glue all the bounded finite index that can be performed in a natural way. So this is the most difficult part in reversing the proposition above. And okay, we introduced this connecting property. If we have an abelian group, and we say that the group scheme has this connecting property, if for any abelian group G exists a copy of G in this guy here, which is exactly the set of finite conjugation class inside this one. This is, of course, a subgroup. And we have the proposition here. If we have an affine group scheme, in few words, if you have an affine group scheme satisfying the connecting property, then you have the analog for Passman's result in this case. So you have here the complete result. So you require this group here is abelian, and for even more morphisms, you have that this guy, this affine group scheme, preserves the finite conjugation class. So if it satisfies the connecting property for abelian subgroup schemes, then you got the analog of Passman result. So in a certain sense, finding group schemes, the definition of polynomial identities for affine group schemes, in a certain sense, fits properly. The problem is that the class of examples of affine group schemes satisfying such property is, how to say, is well, it has to be enlarged a bit, but in a certain sense, seems to work properly. So, as I told you, here we have, in this talk, I would like to show you point of views new point of views for the theory of PA algebras and geometries arising from these new definitions. So of course we have weak points and strength points. As I already mentioned, we have a very few classes of examples satisfying the gluing property. And in a certain sense, they are also unnatural, such conditions. And of course, in order to understand the structures of affine group schemes, you need, of course, a complete list of subgroups of this guy, which is not an easy remark. And of course, why one needs to study this argument. The definitions of polynomial identities related to the combinatorial theory can be, of course, applied to this kind of functor. I mean, the affine group schemes, and also with other kinds of functors. So we have a lot of work, at least a lot of experiments to be done in order to go further with this line of research. Okay, let's go further. And I would like to focus on the geometries arising from varieties. Well, of course, in the first part of my talk, as of course a geometric sense, because I was talking about affine group schemes, which are central objects in algebraic geometry. But with the second part, I would like to go deeply inside the title. So let me forgive me a bit, and I would like to introduce the term geometry as a ring space. Ring space is a couple where this guy here is a topological space, and this guy here, which goes from the category of open sets of X to another category, C, is a sheaf, so that the stalk Fx is a local ring. So from now on, our definition of geometry is exactly this one. Our environment. What is a sheaf on a topological space? It's a functor, as I explained to you previously, with some spatial gluing properties. So in this talk, it's not useful to go far into details. And a stalk on a sheaf is simply this filtered colimit. Of course, one of the tasks is finding the existence of this colimit of the stalk. So my idea here is going on step by step. First of all, do you remember what varieties are? A variety, I would like to recall you, is simply the set of all algebras satisfying the identities of a fixed algebra. So our first question is, can we categorize varieties? Yes. The objects are simply algebras belonging to our variety, and morphisms are the usual morphisms among them. Can we build up at least one sheaf using this variety? Yes, here it is. If you have a variety of, for example, R algebras over R, and U is an open set of X, you consider this one, the tensor product of A with the set of all C infinite functions from U to R. Well, whenever you have this guy here, and you construct this OAX is a sheaf. And what about stalks? Yes, they can be built up naturally without any problems. Let me show you how to construct them. So you have a functor, you consider all this guy, and you quotient, and you put this equivalence relation. Let me explain a bit how does this equivalence relation work. You have two open set of a point x in x. You take S and T belonging to Fu and Fv, and of course, they are equivalent if there exists another neighborhood of x, so that W is in the intersection of U and V, and the two sections S and T do coincide. Of course, the identities of the stalk do contain the identity of A. And the explanation here is somewhat technical, but it's at least important to show you how, because this make you, how to say, it is easy to see and to figure out how this definition will work in our environment. So you have an identity for our algebras, and you take all this guy belonging to the stalk. So you take S1x, S and X element of the stalks, and of course jointly to the choose of all these SIs, you have some open sets neighborhood of X. So of course, you simply take the intersection of all these guys. And of course, when you evaluate F on the elements of all Fx, this is simply the equivalence class of F evaluated on the S1, V, S, and V on all the restrictions. And these guys, of course, because F is an identity of A, turns out to be 0 here. Of course, it is the 0 of the stalk. So you see, the identities of A are exactly inside identities of the stalk. So doing this way, we're able to include to any algebra A geometry, because we have a topological space and a shift determined by the variety generated by A. This is a remarkable point, because this gives you, how to say, something endable when you study PA algebras. This is also another remarkable fact. Do you remember the free algebra I introduced you some slides ago? Well, if you consider this guy free, if you take any variety and you consider this guy here free nu of U, being the relatively free algebra of identity of Fu, where of course X is a countable set of indeterminates, this of course defines a shift. So another geometry on V. So at the moment we constructed two kinds of geometries using a PA algebra. Okay, I would like to tell you why we defined such kind of geometry. Because of course, the classical algebraic geometry is simply a couple of a ring space where you have a sheaf in a variety of commutative algebras, and supergeometry on a certain variety is, of course, identified the ring space XG, which is a sheaf on the category of supercommutative algebras. Supercommutative algebras can be, you can imagine them as Z2 graded algebras in which the homogeneous element have a supercommutative property. Well, they commute if one of the two guys is in the zero part, and they anti-commute if they are both in the odd part. Simply these guys. So the problem is, the geometrical problem is the following: how to reconstruct the classical algebraic geometry of an object if you're studying super geometrical stuff on the same object. Yes, this is possible, to go from the supergeometry to the classical algebraic geometry. So the idea is, okay, how to generalize this fact? Of course, we took any PA algebra and we construct a new geometry, simply categorifying the idea, the notion of variety of algebras. So because of this fact, I mean, we can go from supergeometry to classical algebraic geometry. Our next point was how to go from a geometry to another one. Are they related? And this is our next challenge. Okay, a geometry can be described by geometry XG if there exists a morphism between two sheaves. What is a morphism between two sheaves? Okay, you take an inclusion of open subsets, so X, and the next diagram commute is more or less a natural definition. So we have this result in this direction. This is exactly the generalization of passing from supergeometry to classical algebraic geometry. And this is the next one. You take a topological space, consider two structures of locally graded ring space on X. The first one is XF and the other one is XG. Try to imagine XF is classical, XG is supergeometry. The variety generated by B. So suppose you have this inclusion of variety. And suppose for any V included in U, this restriction coincides with the restriction GU. This is something technical. It's not that easy to find or easy to verify. So there exists a morphisms or ring space from XG to XF. So as I told you, if you have a morphism, you have you know how to reconstruct a geometry from a weaker one. So in this case, we have the following, which is simply a generalization of what we said before. Okay. And of course, as I told you, this the last proposition generalizes what is already well established in the algebraic geometry. So the classical one comes from supergeometry. And simply because the identities of the commutative algebra can be seen as graded identities for the infinite dimensional Grassmann algebra. As I told you, what is this supergeometrical guy? Supergeometrical guy is somebody who is Z2 graded, and the elements of degree 0 do commute. If you have one of the two guys, which is of degree 0, they commute. So, in a certain sense, if you have the zero component is commutative. And of course, algebraic geometry is geometrical stuff, treating objects which are in a commutative environment. And simply, these questions links the two guys. classical algebraic geometry to supergeometry. And in my opinion, this is a very nice point of view for a new study in um, in the environment of non-commutative geometry. Of course, what I wrote here, of course, fits properly also in a non-associative case. We have also another results related to this argument. We recall that R and S are said to be Merid equivalent if their categories or modules are equivalent. This is simply a corollary, but this is the only thing that should be performed only at the moment in an associative environment. This doesn't work in a non-associative case. So if you have A and B Merid equivalent, and as before, you take a topological space and two structures of local ring space on X, as before, XF and XG, in the variety generated by NB, XG in the variety generated by NB, and XF in the variety generated by A, and you have the same technical condition as above, then we have a morphism of local ring space from XG to XF. This is also an interesting fact. So again, what are weak points and what are strength points? Weak points. We do not know how combinatorial PA theory is ruled here. And of course, some topological conditions, of course, will be lost under non-commutative hypothesis. So, well, I don't know. I do not know how the topological condition can be used here in order to to study in from a different point of view this theory. But of course, we have strength points. Several results in differential and algebraic geometry can be tested in new settings. For example, you take any algebra, you construct this geometry, and you would like to study how the geometry works in this environment. This can be done for any algebra here. And so, again, a lot of work. Why? Okay, I would like to close my talk studying the so-called embedding theorems. And this is my third point of view for my talk. General and classical problem. We have a ring and would like to study conditions on R in order to be embedded in the ring S. This is what we call embedding problem for rings. Maybe somebody here knows this problem in a different word. If the ring S is a matrix ring enters with a commutative one, this embedding problem is nothing that a representability problem in an associative case. Simple this. So we go further. I would like to show you what are we gonna study. Of course, well, I do not lose what I wrote in my title. So the motivation is the increasing importance of supercommutativity in a geometrical setting. So we have this problem. We have an algebra. How to embed it in the tensor product of the tensor S, where S is supercommutative. Okay. Simply imagine the infinite dimensional Grassmann algebra. You can think about E as an associative version of the classical Grassmann algebra. And of course, we have this theorem. take a variety and consider A being a finite-dimensional central simple algebra. Central simple algebra means algebra which associative center coincides with the field. And simple, okay, simple is the classical notion of simplicity. What I would like to point out and highlight in this third part is that everything we are saying here, again, fits perfectly in a non-associative setting. In fact, this has been done in a non-associative setting. So, consider finite-dimensional central simple algebra. Suppose A tensor E is in this variety. For all B in this variety also, there exists a superring and a homomorphisms, so that the entries of the elements of this set generate the algebra SAB, and it also has a universal condition. What are the entries of the elements? Okay, you have an homomorphism here, so you have linear combination of something here, and this something here as an element of A and element of SAB. So the entries are exactly the elements of SAB arising from this homomorphism, simply this. Of course, you have a homomorphism, but if we go back to our first definition of embedding problem, we would like this homomorphism is injective. This guy here is called universal supermap, and of course, we are done. We achieved our goal if this guy here turns out to be injective. In order to do this, we need something, we need to construct, to build up something similar to a trace. Okay, in order to construct this trace, we start off with a Z2 graded algebra having the center, ZA, and we denote this generalized commutator by this guy, and the generalized associator as this guy. So, a linear map is called supertraced from A to the center if it satisfies these properties for all homogeneous A, B, C in A. Of course, an algebra with supertrace will be called supertrace algebra. The idea, besides the construction of supercommutative algebras, is something technical. Of course, I would like to share this with you, but no pretension to be exhaustive. Consider a variety of Z2 graded algebra. Consider its free algebra. And we simply try to construct a supercommutative associative supertrace here generated by these symbols. Then we go further and we consider the algebra free new STR generated by this guy and the algebra and the free algebra. So, well, of course, we do need something more. The elements here are to be supercentral. This will play the role of the scalars inside the trace. In few words, we are constructing a new algebra having as coefficients, as scalars, the element inside this guy. And finally, we consider a subalgebra of what we constructed simply just before, generated by all elements strg and g. We have this result. Consider a power associative graded algebra. A is finite dimensional and central simple in the ordinary case, and B is a graded algebra with subtrays belonging to the same variety as A tensor E. And of course, let's find all their identities. In this case, we have our row, our first homomorphism that always exists is injective. And we also have how to figure out how this guy is. So we have a perfect description of the homomorphisms here. We have some sketch of proof also in this case. You consider as free supercommutative associative algebra. Consider, of course, as usual, it's relatively free stuff. We have that the algebra B satisfies all the supertrace identities of this guy, and so we have it is isomorphic to the T over E for some supertrace ideal of T. Then next step is embedding this guy in A tensor delta S, and consider this guy here as the ideal of A tensor delta S generated by E. And we have also, of course, an induced map now from B, which is represented by T over I, and now this quotient here. This map here is surjective, and you also have this relation. And you have finally this equality here that shows you that your map is injective, and this is what we have. We also have a related results saying that in the hypothesis of the previous result, supposing B being a finite generated algebra generated by K elements, then its Kelvin-Kirillov dimension can be bounded from above by K times the Krull dimension of A. And this is also these results coming from the embedding theorem. And we also have a more geometrical object to be put into the recipe. Say B is formally smooth if for any algebra here U in V and any graded nilpotent ideal N in U, we can lift any homomorphism from B from UN to B from U to B to U. The formally smoothness is a generalization of Grothendieck's definition given several years ago. And also we have such a result. We have a power associative algebra so that A is finite dimensional central simple and satisfying the same hypothesis of the previous theorem. And if you consider this guy here, well, this is formally smooth if and only if this guy is formally smooth as superring. So this is the geometrical connection. Okay, it's now time to list again weak points and strength points of this third point of view in this geometrical approach of PA algebras. Again, combinatorial PA theory and what are its relations with this how they can improve the study of this matter. Okay, it's still unknown and at a very germinal state. But what I'm sure to to say is the following: this supercommutativity, for example, can be substituted by some ad hoc operators, as in the Bayes work. And also the fact that concrete cases in a Lee or Jordan context, I think, can give out interesting results, and also with immediate approach. So I think I finished, and I would like to also to say the first of the 3 point of view was along a paper of mine. The second one is a paper written with Mauricio Correa Barros, and the third one with Charles Almeida and Claudemir Fidelis. And it's all. Yeah, I'm finished.
Thank you. Thank you very much. I have some questions. So, from the beginning, you consider PI algebras, polynomial algebras, over fields of zero characteristic, yes?
Yes.
But what about finite fields or something like this?
Well, in general, problems with finite fields, or fields with a characteristic different from zero, is related to using different kind of polynomials. If you have characteristic zero, you can work with multilinear polynomials. If you have characteristic free, you can work with an infinite field. You can work with multi-homogeneous polynomials. So the problem is exactly here in using different kind of polynomials. Of course, working with multilinear ones is much better than working with other class of polynomials. And try to imagine that, for example, it's unknown the set of polynomial identities of matrices of two by two matrices over an infinite field of characteristic 2. So we have some concrete cases of the fact that working in characteristic zero is much better than other cases. But of course, as a counterpart, you have working with characteristic free is something, of course, is interesting. It has a lot of difficulties. So this is, I think, is the answer to your question.
And what about if you take algebraically closed field? Will there any deeper results?
Yeah, of course. Yeah, of course. Especially in the combinatorial part of POE theory, you need to use algebraically closed field. Because it's simple. It's simpler to use to achieve results coming from the representation theory of the symmetric groups. So is exactly this the problem?
Thank you. Please, more questions or comments? I see no. So thank you very much, Lucio, for very
thank you for the opportunity and
very interesting problems. Thank you.
Thank you. And good work to everybody.
Thank you. So we are finishing the first session of our seminar, and we have a break for 1 hour. Yes, Jobber? 1 hour.
1 hour.
For
yes,
the,
1 hour.
For the next part of our seminar. See you in 1 hour. Bye-bye.